So I'd like to start by just mentioning that I have created a calculated column on Blackboard that shows your current average, including all the assignments and excluding the final exam and homework 7. The idea there was that I have no idea who's planning on taking this course pass-fail. But if you're planning on taking a pass-fail, you can kind of see where your current grade stands if you were to not do anything else in the course. So all you need is above a 60 to pass. And so just gives you an idea of what you might need to get on the next couple assignments to pass. Some people could stop right now if they're taking a pass-fail. Other people still need to work towards getting a passing grade. I have not yet graded homework 6. I was hoping a couple more people would turn that in so I could grade them together, but alas, that has not happened. So I'll probably look to grade those potentially today. And all we have really left in the course, homework 6 was due, homework 7 is due next week, and then we've got the final. My plan here is to do 6.3 today, 6.4 on Thursday, 6.5 next Tuesday, and that's it. I'll pass out the final exam next Tuesday, and you'll have a week to complete it. It'll be due Tuesday the 12th. So we can spend the last 2 class periods. We can just, if you want, meet during this time, and I'm happy to answer questions about the test. I think that's all I wanted to say. Can I answer any questions about anything before we get started?
Yeah, you're gonna be around after this class to talk about homework a little bit?
I can be around after class to talk about homework. Yep.
Okay.
Other thoughts, questions? Okay. So this is the PDE section, which is partial differential equations. We spent some time talking about what that is, and you might be wondering why this section's titled linear ordinary differential equations. So we use some concepts from ODEs, or ordinary differential equations, to solve some of the problems that lie within a PDE in order to obtain the full solution to a PDE. And so we're going to talk about solving linear ODEs, today, again, to help with solving PDEs. It's also just a good thing to know how to do if you're going to be an applied person. And so I'd like to start with reminding you a quick thing about separation of variables. If you've had a class with me, I know maybe Bradley and Nick saw this or something similar to it in a previous class with me. Maybe Danny hasn't. So if you have an ODE, y prime equals y, and let's assume that y is a function of x. That's called an ODE because there's only one variable, right? There's like the input is x and the output is y, and there's only one of the input. And so we would think about this as like dy dx equals, let's do it, let's make it r times y. Yeah, so some rate times y, where r is a constant, some constant rate. If you've got a nice, easy differential equation like this one, then you can use separation of variables to solve it, where you get the things with an x in it on one side, which would be the y, right? The y has an x sort of inside it implicitly, and you get everything else on the other side, which would be the r, and then you can integrate. And so we can use separation of variables to solve this one. And this is going to apply to what we're about to do, which is why I'm doing that. Is that really bright? Can you see that? It looks weird on my screen. Sometimes I like to sign in on my other computer here just to see what it looks like. Hold on a second. It's kind of bright. Turn this light off. I think that's the best I can do. Let me know if you can't see that. Let me actually put one more thing up here. This might help. don't know, maybe that helps. Anyway, so we separate variables by doing this. 1 over y dy equals r dx. So everything with a y in it is over to the left side, and the things that are either not a y or an x are over on the right. And then the whole point of doing that is because then you can integrate both sides. You can just put an integrand on both sides, and this only has a y, so you can integrate it. This only has x's, or in this case, a constant, and so you can integrate it, and it becomes a problem that you're able to integrate, right? We want the solution to y, right? We're given y prime, so we're trying to find y, and this is how we're going to do it. So the integral of 1 over y is ln y, and then over here you'd get rx plus c. And they both get a plus c, but let's just assume we collect the constants on the right. Well, how do we solve this equation for y? Well, this is log base e, and so the way you do log equations, just taught this in pre-calc today, is you do e raised to both sides. And it cancels out on the left because you've got a natural log, and then the thing on the right gets raised to the power, gets raised into the power of e. So it becomes this, in other words. And that's the solution for y, right? This is y of x. We were given the derivative of y. Let me see if I can fit them both on the same screen here. We were given the derivative of y, and we separated variables in this simple problem, and we're able to solve for y by itself. Now, we can sort of adjust the way that that looks to make it look different. So, for example, you can break this up into e to the rx times e to the c. Right? It's like you have two like bases, and so you'd add the exponents to get that. And then e to the c is just some other constant, right? E is a constant, c is a constant, so e to the c is a constant. And so you could really think about this as some constant e to the rx. Right? So this is like the solution to y using separation of variables. But the reason I wanted to show that, let me zoom in again, maybe it'll help the lightness. I don't know if you're having a hard time seeing that. The reason I wanted to sort of remind you about separation of variables, or maybe show it to you, is that if you have a simple equation, this is easy to do, and we can see that solutions to these ODEs are exponential. That's the thing I really want to point out. Notice that the solution is an exponential. So the solutions to ODEs, or even systems of ODEs, like in my own research, like I know I gave a research talk in Danny's seminar earlier this year, and actually the other folks heard a similar research talk of mine recently too. Then you all know I use ODEs in my own research related to disease spread. And when you're hearing people talk about coronavirus spreading, they're also using ODEs most of the time to talk about that. Anyway, my point is solutions to those systems are also exponential, which is why they're talking about like flattening the curve and things like that, because solutions to these ODE models that they're using are exponential. And we want them to be exponential because the disease spread is an exponential thing. But anyway, the point here is solutions to ODEs are exponential. And so that applies directly to our next page, because when we have an ODE, in order to solve it, we assume the solution is exponential, right? We assume the solution we just found a second ago, and we end up plugging it in. And I just wanted to start off by showing you why we assume that it's exponential. It's because when you solve these ODEs, you get exponential solutions. Thoughts about that at all? So, okay, so here's a general ugly ODE, right? So the one that we just looked at was super, super simple. It was just y prime equals y, right? This one is showing you a bunch of coefficients. So the AJs are constant for all j, so they're constant coefficients. And then the y's are the state variables. And each one of these n's, like in the exponent, these are actually derivatives. So all these things up here in what appears to be the exponent of y, these are the nth derivative. And so, you know, example of one would be this right here, right? So this is like y double prime minus 3y prime minus 18y equals 0. And so this follows that general form with n equals 2 in this case. And so we call these constant coefficient differential equations, so the n's are constant. And what we do in order to solve them, right, solving linear second order constant coefficient ODEs, is we assume the solution is exponential, we plug it in, and then we come up with a solution based on the characteristic equation. Because we know it's going to be solution, it's going to be exponential. Excuse me. And so that's what we're going to do right here. So we assume the solution is exponential. And then if we know that y has this exponential form, then we can take derivatives of this and also plug that into y and y prime, right? So for example, if we're assuming that y is going to have an exponential solution, then that means the derivative of that would be this, right? It's a chain rule problem. You take the derivative of e to the rx, which stays the same, and then you multiply it by the derivative of rx, which is r. And if we did it a second time, it would just be, you do the same thing again, and you'd multiply by a second r, and you'd end up with that. And so in other words, we can replace y double prime, y prime, and y with those three things. And so let's do that. So let's plug those in. So this expression right here, set equal to 0, becomes r squared e to the rx minus 3 r e to the rx minus 18 e to the rx equals 0. This spacing on this page is a little messed up. I need to edit this one. So we're probably going to write down here along the right-hand side of this page, and then I'm going to write some more stuff on the left-hand side under initial value problems. Just be aware of that. Anyway, so we want to solve this equation. We want to figure out what these r's are, right? Because we know the solution looks like e to the rx, and so we're really trying to figure out what r is. And so let's try to solve this equation for r. And so each one of these terms has an e to the rx, and so we can factor out e to the rx and obtain this. And now we set both of those things equal to 0, right? We set e to the rx equal to 0, and then the polynomial we set equal to 0 as well. Well, we know that exponentials never equal 0, right? They have that they have a horizontal asymptote at 0, so they never actually get down to 0. And so what we really need is we need the polynomial to be 0. And that's a nice, easy problem to solve, right? You can use a quadratic formula or factor it, whatever you need to do to solve that. And this is something that we should be aware of. This has a specific name. This is called the characteristic equation, which is a different characteristic equation than obviously you get when you're finding eigenvalues and eigenvectors, but it does have the same name. So anyway, we can factor that pretty easily in this case into r minus 6, r plus 3. And so we see that r is 6 or negative 3. And so we know the r's that need to go into this equation, the e to the rx thing, except we have 2 of them. And so we assume, or we know the solution then is the following. Y is the sum of those 2 things. So some constant e to the 6x plus some other constant e to the minus 3x. And we refer to that as the general solution. In other words, general means it has constants in it, right? It's not specific because we don't know what the constants are. And so this gives us like a family of curves, right? So C1 and C2 are just some constants. And so when we plug different constants in, it gives us different pictures. And so we have like a general idea what the picture looks like with the exponentials in their r's, but we don't really know the constants, which is why this is the general solution. Okay, I'm going to talk about the initial value part of that, but are there questions about any of that work there? Okay. So in order to find C1 and C2, we need at least two pieces of information about the function, right? In other words, we've got two unknowns, and so if we want to figure out two unknowns, you need two equations usually. And so usually that's given to you in the form of some information about y or some piece of some piece of information about its derivatives. And that's what's called the specific solution when you find that. So to find C1, C2, or any constant that you end up with, we need information about y and its derivatives. Most of the time, you're given usually it's initial values and something about the derivative at t equals 0, right? So usually this info is in the form of initial values. This is very similar to the situation that when you're in calculus and you integrate something and you end up with a plus c, how do you find the plus c? Well, you're usually given some piece of information. It's just now we have two c's, and so we need two pieces of information. So initial values, another way to say that is initial values, or in other words, values at the initial time. Whatever the initial time t equals 0 is. So for example, oftentimes it'll look something like you're given, let me rewrite this problem. Where did it go? Y double prime minus 3y prime minus 18y equals 0, right? That was the original problem. And then below it, it'll say something like where y at 0 is some value, a, call it a1, and the derivative at t equals 0 is some other value. And then what you would do is you would use these two pieces of information to create a system to find C1 and C2. I've looked at things kind of like this before when we were trying to find constants previously. And this is a very, very similar to mathematical modeling last semester, where we were finding solutions to difference equations, except we're just doing differential equations now. So we're doing a continuous version of what we did last semester for those who are in that class. Okay, thoughts about that at all? We're going to look at a couple particular solutions here, do some examples, call it a day. Questions so far? So I know I have the following three examples bunched up on one page. They should really probably be spread out to three separate pages. So I just spread the following three to separate pages. You will need additional pages to probably answer all those. I'm sorry that those are on the same page there. So this is the first one that's on that page, and it's the exact same one we just solved on the last page, right? With some of those initial conditions that I was just talking about. So we have some value of the function at 0 and some value at the derivative at 0. And so this question says find a particular solution, and particular solution just means find what the constants are. Find constant C1 and C2 from the last page. And so on the last page, we found this. We found that the general solution was this, right? Well, we can take the derivative of that. Why are we going to take the derivative of that? Because I have some information about what the derivative is at 0. And so we take the derivative of this, and we'll have two things to plug 0 into, and then we'll be able to create a system. So this was from the last page. That's a general solution. Well, that implies that when you take the derivative, it's another chain rule thing. So you get C1 6 e to the 6x plus C2 times minus 3 e to the minus 3x. And then we know what happens to each one of those things when you plug 0 in, right? This is what this is telling us here. And so the fact that y of 0 equals 3, what you do with that then, this first piece of information, is you plug in 0 here, and you set it equal to 3, right? And so that means that, and when you plug in 0, you get this, of course. And those just go away. Those just equal 1. And so you'd get that equals 3. And then you know the derivative at 0 is negative 4. And so that means this. Oh, at 0, though. Sorry, I forgot to plug in 0. Not equals negative 4. You got to plug in 0. My fault. Trying to plug in 0, not negative 4. C2, I'm going to make the negative right here. So it's minus C2 times 3 e to the 0, and that equals negative 4. So you get two systems, or two equations, right? You can create a system, easily solve that system. This first one is telling us that C1 plus C2 should be 3, and the second one is telling us that 6C1 minus 3C2 is negative 4. And so two equations, two unknowns, very easy to solve. Put it in a matrix if you want, or you can just do back substitution or something on this one to get that, right? So I guess let me just to be clear about it in case people are still confused, right? You could take the first equation and say C1 equals 3, negative 3 plus C2. No, 3 minus C2. My goodness. Algebra. And then you could plug that into the second equation and get 6 times 3 minus C2 minus 3C2 equals negative 4. And then obviously you can find C2. And then once you have C2, you can use that to find C1. I won't belabor the point here. I'm confident you know what I'm talking about. Let me know if you don't. But when you do that, you find out that C2 is 22/9 and C1 is 5/9. And so when you plug those into the general solution, you get a specific solution. So, and it's all dependent on these initial values, right? Without that, we wouldn't be able to get that. And so our final specific or particular solution, excuse me, sometimes it's called specific solution. That's another way to say it, is what we wrote down with those plugged into the C. So y equals 5/9 e to the 6x plus 22/9 e to the minus 3x. That would be a particular solution. That's the general process. Thoughts about that? All right, wonderful. So there's a couple more examples here, and the idea here, notice what we got here. We had two unique solutions to, I'm sorry, where am I looking here? Oh, on the last page, of course. In this particular problem, when we solved the characteristic equation, we got two real distinct values, right? R equals 6 and negative 3, and that led to a form of a solution that looked like this. If you look 2 pages down the line, or I guess it's technically it's on the next page in your notes, there's a list of all the different possibilities that might happen, right? If you're given a general system that looks like this. We just saw example number 1. We saw R1 and R2 being real distinct values, and so the general solution ended up looking like this, right? So this is exactly what we just saw in example number 1. And so examples 2 and 3 go through some other scenarios where we either get a repeated root, or we get a root with an imaginary number in it, and we'll see what happens with those two things. So basically, we're going to kind of derive these solutions that are in this lemma in the next couple examples. That's the idea. I usually, in the past, have sort of split people up and let folks work on these together, but given the amount of participation I've had in this course, I'm not going to risk that today. And instead, I'm just going to try to rifle through these and see if they make sense. We'll try to drive those things. Please let me know if they make, if you need any help or if you have any questions about it. So in this first one, y double prime plus 16y equals 0, you plug in y equals e to the minus rx, right? And in that case, you take the derivative, because we need the second derivative here. The first derivative would be this, and the second derivative is this, right? And so we plug y and y double prime into this one, right? So this one's missing a y prime term. And when we do that, we would get r squared e to the rx plus 16 e to the rx equals 0. We factor out e to the rx, just like the last one. And we have r squared plus 16. And then, of course, r squared plus 16 needs to be 0, and we end up with an imaginary root, a double imaginary root, right? So r is going to end up being plus or minus square root of negative 16, which is plus or minus 4i. So we get two purely imaginary roots here, right? In other words, there's no real part. Sometimes you have like a real number in front of here, like 2 plus or minus 4i or something. This is purely imaginary. And so this is going to be one of the cases on the next page, you'll notice. Case 3. And so we should see that we end up with the form in case 3. But let's walk through the process of it. So let's assume, let's just do exactly what we just did, right? So we know that then the solution is c1 e to the rx, so 4ix plus c2 e to the minus 4ix. That's exactly what we just did a second ago. But we spent a bunch of time this semester talking about how these e to the I things can be written as trig functions, or really what we had been doing is talking about how trig functions can be written as e to the I. But we know that now, right? So we know e to the ki theta equals cosine k theta plus I sine k theta. That's the thing that we sort of introduced pretty early in the course. And based on that, we also know things about even and odd with cosine. That's right. So we also know that like cosine is even, so this is true. And we know that sine is odd, and so we know this is true. And so we're going to, change the e to the i's into sines and cosines. Some of them might have negative x's in there because of this negative 4, and so we'll know what to do with the negative x's in whether it's in a sine or a cosine. That's sort of where we're heading towards. Just going to pause there for 1 second and see if everyone's with me. Feel free to stop me at any time, but I'm just going to see right now. Okay, so given this information, we can take this solution and change it into this. Ooh, do I have enough room? Yeah, that should be fine. C1 cosine 4x plus I sine 4x plus C2 cosine minus 4x plus I sine minus 4x. Right, so just using that property, right, the first line, that is, I'm taking each of the e's and just making them into sines and cosines. And then we're going to use the second properties here about, even and odd functions to deal with these two terms right here, right? So we know that this just becomes cosine 4x, and we know that this one, the minus sign can kind of move out front. And so the first one stays the same, though, so this doesn't change. I'll stop writing parentheses. I hope that's all right. When you do something like that in pre-calc, when like you write parentheses around 4x inside sine, and then all of a sudden you don't, people really confused. And so I try to be careful with that, but I think you guys probably know what I mean there. Anyway, so this one changes to the positive. Oops, I just drew the parentheses. And this one, the minus sign moves up front. All right. Thoughts? Seems okay so far? Okay, let's group the sines and the cosines together, right? We've got a couple cosine 4x's and we have a couple sine 4x's. And so let's group those and factor them out. So this is going to be C1i minus C2i times sine of 4x. So that's the two coefficients in front of the sines, right? And then C1 plus C2 cosine 4x. And I just changed the order of them because I want it to look more like it does on the next page. Well, it turns out that C1i plus C2 or minus C2i is just some other constant, right? And C1 plus C2 is some other constant. And so we could just write this as C3 sine of 4x plus C4 cosine of 4x. Oops, I'm off page. And so if you look on the next page, this is the general solution that we get when we have two purely imaginary roots. Right, that's exactly what this one says right here is if number 3, if you get two roots that are purely imaginary, then the solution is going to look like this. And this is exactly what we just saw in example number 2. But again, you follow the same process we did before, but then it's just like changing the e's to sines and cosines because you have i's in there. And then you end up with this sine cosine version. Thoughts about that at all? All right, wonderful. Let me do the next one then. So there's one more example on that first page, which is this one. And I'm going to do this one a little bit quicker without so many details here. So this has, I hope you'll be with me, what ends up happening is for the characteristic equation is you can basically change the y primes to r raised to a power, right? So like y double prime becomes r squared, y prime becomes r, and y just becomes y to the 0, right? So in other words, after you plug in e's and you factor everything out, the characteristic equation is going to be r squared plus 6r plus 13 equals 0. I hope that makes sense, right? If we just like look back at the last one, for example, we had y double prime of 16y, and then the characteristic equation ended up being r squared plus 16, right? So you kind of like change these things to powers where y without a derivative just goes away. And that's a characteristic equation. Is that okay? Are there questions about that? So this one is not nice to factor, right? So we can use the quadratic formula on this one instead to get this. And when you simplify that down, you would get minus 3 plus or minus I have 2. Oh yeah, 2i. That's right. Is that right? 36 minus, that's going to be 4. Yeah, plus or minus 2i. And so those are the r's. And so this is slightly different than the last one because we don't just have imaginary numbers, but we have a real part attached to it, right? So we have the minus 3. Last time we just had the imaginary. So it's slightly different, and you'll see how it's different when we actually try to do this, right? So we're going to plug things into this, where this is our R1, R2, and we get a more complicated expression because now all of a sudden we have this expression in the exponent. But actually, it's not that bad because we can see that both of these things have an e to the minus 3. Actually, has an e to the minus 3x. And so you can factor out the e to the minus 3x out of both terms and end up with this. And now this thing right here is like exactly what we had on the last page, right? This part is. And it just has this other thing out in front of it. And so we can use the Euler's formula on that piece. And we'll get the same solution sort of similar to the last page. It's just then going to be multiplied by this constant out front. Right, so when we use Euler's formula from the last page, Euler's formula, by the way, is this thing. We had to find it as Euler's formula when we first looked at it. So this ends up being, once we apply that formula, it'll be e to the minus 3x c3 cosine 2x plus c4 sine of 2x. And these are different constants because after you go through that whole thing we just did in the last page, you end up with something that looks like this. Right? You get like c1 minus c2, and you just make it into a new one. All right, so I'm going to pause there. See how that looks. Let's cut that at all. So the idea then is just that we've derived three out of the 4 of these ones at least. We didn't look at all of them, but we've derived 3 out of the 4 of these lemmas, right? So this lemma says, and it's called lemma 6.1. Keep that in mind because some of the homework says like, oh, use lemma 6.1 to do this, and so this is the lemma you would want to use. So it says when you have a second order ODE. So second order. Does anyone remember what that means? Love to hear someone's voice. What does second order mean?
Is it like second derivative?
Yeah, there's 2 derivatives. Right, so the order is the highest number of derivatives that have been taken. So in other words, you've got a y double prime. So when you have a second order, i.e. you have a y double prime situation, the characteristic equation is going to be AR squared plus BR plus C equals 0. Right? That characteristic equation is going to look like that. And this sort of tells us what to do based on the roots. So if we have 2 distinct roots that are different, you get what you got in example 1, which is a nice sort of linear combination of exponentials. This is the one we didn't see. If you have a repeated root, so if we got like r equals 2 repeated, so r1 and r2 are the same, then you get a similar version of this one, but you'll just have to basically factor out the common term. In other words, there's an extra x in this, right? So this x is extra. That's not in the one above it. So we didn't see an example of that, but you might be able to see one of those in the homework. If you get purely imaginary ones, you get the sine and cosine thing. And if you get imaginary ones that also have a real component, this is what we saw in the last example, example 3. You get, again, the Euler kind of looking thing, but then you get the extra term out front. All right, so there are a number of questions like this in the homework. And what you need to do, you don't need to do exactly what we did in the last page. Like, you know, I wouldn't recommend finding the roots, plugging them in, using Euler's formula, blah, blah, blah. Instead, what you can do is you can just find the roots and then use the lemma. So this one would be like, okay, this is which one of those would apply to this. Oops, I put the wrong page up there, sorry. Is that the wrong page? Let's just do that page. Oh, it's right below it. I would say, oh, look, this one has A plus or minus BI. And then I would go right to here and say, okay, well, this is what the solution is going to look like in that case, right? The alpha goes in the alpha spot, and then the beta would go in the beta spots. And so it's a nice sort of quick way to jump right to the solution. And so I would like to ask you to try the last couple. And so again, I actually just edited this one. I apologize. This page is a little bit of a mess as I was looking for it. So these are 2 new questions. And I'd like to pause for a couple minutes and let folks try these, right? So use the lemma to find the general solution. So in other words, 1, write the characteristic equation. 2, solve for the r's. 3, use the lemma to write the form. These should basically take you as long as it takes to solve 2 quadratic formulas. So I'm going to ask you to try that. I can't force you to do it, but I am going to sit here in silence for, I don't know, at least 5 minutes and see what you got. Maybe I'll sort of start slowly writing them in just a couple minutes, but I'm just going to pause here, and I'd really encourage you to try it. Just give it a go. And maybe I'll either wait for 5 minutes until no one said anything and then come back, or heck, if you finish, it'd be cool if you would just say it in the chat, and then whenever people are done, we can look at the answers. Let me know if you have any questions. Spend a couple minutes on that. I think I'll just sort of slowly start writing the answers here to both of them together. Let me know if you have any questions. I am going to go real slow and sort of hope that you're working on this. Any questions about the roots at all? Hopefully that's okay. So this first one then, this is, this looks like this case. This looks like case 4. And the second one looks like case 2, where you have the same root. And so I'm going to use case 2 and case 4 on these. So dilemma 6.1, number 4 on this first one, y equals e to the minus whatever the alpha is, which in this case is, e to the whatever alpha is, x, so in this case -2, times c1 sine, and then you put the b's in here. So the b is a 1, right? There's like a 1i right there. So the sine of 1x plus c2 cosine of 1x. And then the second one is case 2. And so we would do case 2 for the last one. Any questions?
Nope.
Someone just said something. That's just no?
Yeah, I was just saying no. Like that's what I got for both of them.
Great. Wonderful. So again, it's generally good just to know about ODEs and how to solve them. But the other reason we're looking at this is because inside of PDEs are often ODEs on the boundary. So you solve like boundary problems using this kind of technique. So we're going to use these techniques. I mean, these techniques are their own thing on their own problems. And in the homework, there are problems that ask you to use this. Like the first problem says use lemma 6.1 to solve these things. And so you do this. But within other problems, like in number 2, for example, where it talks about the Sturm-Liouville problem, we'll use this kind of concept to help with the initial conditions and things like that. All right, so if there aren't any questions, that's all I have for today. I'm going to go ahead and stop the recording and post this.